All right, good morning or good afternoon, everyone, depending on where you are. I'm Chris Spinagle from the Warning Decision Training Division. I'd like to welcome you to today's Storm of the Month presentation. Today's presentation comes to you from right here in Norman at the Warning Decision Training Division. Our presenter is Andy Wood. He'll be presenting on 3 steps to identifying elevation side lobe contamination. With all that being said, Andy, the floor is yours, so go ahead and take it away.
All right. So I just wanted to start off showing this slide talking about this series that we're currently going through. Today's session is the third in a series of 4. So this will be on 3 steps to identifying elevation side lobe contamination, like Chris said. And then next month will be on scanning strategy best practices, which I will also be leading. So just putting out a plug for that one as well. So just for starters, I wanted to talk briefly about training that we have in the radar and applications course when it comes to side lobe contamination. So I've just got a listing here, and specifically we've got 3 lessons in our principles of radar section that get into a little bit of the physics of it and what's going on. But particularly for this session that I'm going through today, I'm borrowing a lot from this lesson I have on velocity contamination artifacts. And so that's kind of the bulk of what I'm talking about is going to be picking up from that and also having some updated details than what's in that lesson as well. So that's kind of the basis for the content today. So as I start, I wanted to talk a little bit about the motivation for this training because this is a topic that has become, I think, more and more prominent, more and more visible over the last few years. And so there's 2 particular papers that I think really brought some attention to it in the recent past. The first was Bentley et al. In 2021. And they looked at 3 years worth of storms that had tornado warnings. And in part of their study, they found that about a quarter of them had some form of velocity contamination. And when they went back and looked at that in a little more detail, they found out about 90% of the time it was some form of side lobe contamination causing the problem. So that's nice low-hanging fruit to try to address through training. And specifically where the problem comes in is that when you have side lobe contamination of some variety, it tends to lead people to overestimate a rotational velocity or VROT calculation that they try to make. And so by properly identifying the side lobe contamination when it occurs, it can lead to a decrease in false alarm ratio. And in their study, they found it was a drop of about 0.8 down to about 0.66, so definitely significant. So after that paper, one of our former instructors, Jamie Boettcher and Bentley, got together and they identified some of the common features and even came up with a 3-step process for identifying side lobe contamination when it occurred. So we've then taken that recommendation and put it into training. So we'll hit the highlights of that here. But before we get into those steps, I do want to give a little bit of background because I know when I talk about side lobes, some folks out there may not fully understand or know what they are. So I just wanted to give a quick refresher on that. This image here shows the antenna wave pattern. Now this image is actually about, I think, 30 years old, showing what the KOUN wave pattern looked like when it was first put out there. And when that wave pattern is designed, it's designed to maximize the data that we see in the main lobe of the radar. So I even have a little area there near the top demonstrating where the half power beam width is, which cuts off at about a 3 dB drop from the maximum. And so that's the data that we're really trying to capture in the radar data. But just in terms of the radar meteorology and just the building of the system, you are going to naturally get these little side lobes at lower power. And so the thing that's important to remember is those side lobes, they're not just horizontal, they wrap 360 degrees around that main lobe of the radar pulse that gets sent out. And so you can have situations where the power return from those side lobes is significant, specifically when whatever energy gets returned from the main lobe is very weak. And when those side lobes interact with an echo that's very strong, that's when you're going to most likely see this happen. And so the contamination usually starts to be noticeable when the difference in reflectivity between the side lobe and what's in the main lobe is about 50 dBz. So just to kind of give you more of a schematic and example of what that might look like, on the right here, I have this diagram showing the main lobe going past a schematic of a thunderstorm where the main lobe is in an area of very weak reflectivity return, but those side lobes are hitting areas of much stronger reflectivity. And so that's where you have a situation where that side lobe is going to contaminate the main lobe. And what it does is all of that energy ends up coming back and just gets convoluted at the radar where it thinks everything is from the main lobe and doesn't realize that the power that's coming back, or at least some of it, is coming from that side lobe. And so the way that can appear in the radar data, at least in this particular image I have in the lower left, that's kind of the classic side lobe example, where when you look off to the side of the reflectivity core, you see this artifact of relatively weak reflectivity and some unusual looking data returns that don't appear meteorological in some of the other base data. And so this is just a sum of all that data that gets returned, like I said. But you end up with these unrealistic artifacts. So specifically when we talk about velocity data in side lobe contamination, the issue comes where the velocity data that comes back, it causes you to think something's going on that may not be going on, specifically in terms of a mesocyclone that could possibly have a tornado. And so I've got this example here of a storm that's located east of a radar. And if you quickly look at that velocity data, you can see that there is a general cyclonic pattern to the velocity data. The problem is that the outbound part of that couplet is located out into the clear air area on the inflow side of the storm where there's not a whole lot of power return, and these locations are the ones that are going to be most susceptible to having some sort of side lobe contamination just because of the nature of the radar antenna pattern. And so if we can spot these situations when they happen, it can definitely help in terms of making better warning decisions. So in terms of the RAC training, we really have a two-step process. First, we try to help folks identify what they call imposter circulations, which are where we have an appearance of a circulation that isn't legitimate, and then try to provide some guidance to folks on what to do when we know that there is an imposter present. So we'll just go ahead, we'll dive right into what some of the common features are with these imposter circulations. And so the first thing we see is they tend to be blocky in terms of the velocity texture. And so this is that same example I was just showing a few slides ago. And so if we look at these outbound velocities, one of the things that we see is it's kind of monolithic appearance. It doesn't have that classic Rankine vortex appearance to it. And so again, just for the sake of folks who, if I say Rankine vortex and maybe they're not the most familiar with that concept, I have this illustration here. So when we talk about a Rankine vortex, what that means is that as you start approaching the mesocyclone from the outside, theoretically, you start to see this slow ramp up in intensity of your velocity data, both in the inbound and outbound. And it tends to reach a peak right near the edges of the circulation. And then as you go to the middle of the circulation, it tends to drop off towards zero. And so you tend to have a tight gradient in the middle and then a more gradual gradient as you move away. And so I have just one actual example of that there in the lower right corner. And you can see how the gradients in the velocity data there don't look like what we see here in that SRM from this example I had in the 4-panel. So that is one characteristic that we tend to see with these imposter circulations. A second thing we tend to see is unrealistic shear. Now this particular example, it's got a couple of different unrealistic looking aspects to the velocity data, but what we see is we tend to get an unusually long area of shear, and sometimes the magnitude is just not realistic. And so in this case, the magnitude isn't necessarily that bad, but you can kind of see how you've got that artificial boundary between two different radials as we move from where the radar is north of the radar down to the south. In addition to that, we also have this weird extra strong convergence zone that just happens to match up with where the reflectivity gradient is on the forward flank of the storm. So this one is doubly complicated in that aspect, but it is fairly common to see those unusual shear zones. So a third common feature is that the circulations are actually located in the wrong place. So it's important to spot the location of these things. So in this particular storm here, we've got nice reflectivity structure with a hook echo and all that. But when we quickly look at the velocity data, the area at first that might look like it has the stronger circulation is actually this area more towards the forward flank and into the clear air. And the outbound velocities, which are still in relatively strong return, actually don't look too bad. But that area towards the inflow, we've got some stronger gates in there, but you can see that there are some issues with the velocity with it being a little noisy and not looking quite right. And again, that's not necessarily where we would expect the circulation to be on the lowest tilt. We really would expect it to be more co-located with the hook. And so that's where we would expect to see the real couplet, not quite so far up on the forward flank. So a fourth feature that's pretty common with these is that we would get unbalanced rotational velocity maxima when we're trying to calculate it. And so an important aspect of this is that you want to make sure that your storm motion is accurate. It's something you want to check relatively frequently. And this is something I know when we're in RAC and talking with people, I try to highlight as much as I can. In this case, I'm using the STI just to get the average storm motion because that's a nice starting point. But I even went back and looked at the warnings that were issued around this time just to get that second opinion, and even the different warnings that were issued for different storms in this area, they all had about the same storm motion, which matched what STI had pretty close. So I feel pretty confident that what I'm using here is a good storm motion. But when we look at SRM, we've got the outbounds of 30 to 45, but those inbounds are super strong, much stronger than that. And so we get that unbalanced circulation. Plus, going back to that feature we talked about earlier, you've got that unusually long shear that it's really stark in terms of going from one velocity to the next. So again, these things tend to happen. They're fairly common what we see in these circulations that are imposters. So a fifth thing is that the circulations tend to be visible at lower levels. And so certainly on those 0.5 tilts is where we'll see them. In this case, the 0.5 tilt, the center of the beam is only about 2,000 feet above ground level. Now, for those of you out there who have those low-level supplemental tilts where you can see even lower, you'll definitely be able to see them on those lower tilts as well. But definitely, just because of the nature of these things, when you're on that inflow side of the storm, where your weakest returns are going to be, are probably going to be in those lowest 5, 6, 7,000 feet, especially if you have like a bounded weak echo region where once you get a little higher up, you're going to start getting stronger returns above it. And so at that point, it tends to go away. And so in this case, just showing this kind of cross-section example again, you can see where the main lobe's pointing. There's not much there in the way of returns, but you've got lots of potential contamination. And so this is where this conversation with side lobes and what we're referring to as elevation side lobes comes in, is because traditionally we've talked about it more in the horizontal, but really everything in that side lobe that wraps all the way around that gets returned will contribute to the convoluted signal that the radar sees. And so that can be anything from stronger returns that are directly above the main lobe, anything at any azimuth around it. It can even be, depending on how far away the storm is, the radar could be seeing things in the side lobes that are actually below 0.5 but still have strong reflectivity too. So there's a lot of things that can contribute. It's like an integral of all of that area that's getting returned. And that's something I think sometimes that gets lost when talking about side lobes. It's also important, like I said, depending on how close the storm is to the radar, not only might you see it on those low-level supplemental tilts, but you can sometimes see it on 0.9, 1.3, depending on how close the storm is. And so that's something to be aware of too. So the last of what I would call the common features is that the contamination tends to be apparent in weaker reflectivity returns. So In this particular case, towards the forward flank, we've got these strong inbounds that at least give the appearance of some cyclonic shear. And all of those inbounds are located in reflectivity returns of about 10 dBz, well away from the storm, which is really not where you would expect it to be. But if you get somebody who is maybe not the most confident, they might see something like this and not realize that you've got a perfectly good circulation back here, which is more co-located with the reflectivity hook with this storm. And so that could definitely mess people up if they're not the most comfortable. So those are all things that I would call common features. Now I'm going to talk about a couple of things that you might see one situation or the other, and that's where it actually comes to the velocity, structure, and texture. And so one of the things that we will tend to see is sometimes we will get noisy velocity data and high spectrum width. And so this example I was showing earlier is a really good example of that, where you still have some really strong outbounds. If somebody looked at it, they might think there's a circulation here, especially when you start looking at this Boeing segment coming out of this storm. Again, somebody is not the most confident, doesn't have the strongest radar background. They might see something and jump on it even though it's not there. But in this case, where the data is noisy and velocity, that's where we have these really high spectrum width values of, say, 20, 25 knots. And so that kind of fits with a situation where you likely are getting returns of similar values competing in what's strongest. And so you might end up, like if you were actually looking at the return power spectrum, like in the level 1 data, you might actually see something like a bimodal distribution, or even worse, like a trimodal, but you're seeing something where multiple things are kind of competing for what the radar thinks is the actual velocity data in the main lobe. So in addition to this, one of the things that we'll sometimes see is we'll also see smooth velocity data and spectrum width data. And so in this case, what we think is going on is that whatever is getting returned from the side lobe is actually dominating. So there's like almost no power return in the main lobe at all, and what's coming from the side lobe is really strong. And because the spectrum width is so low, there's a decent chance that you probably do have one area that's got really strong returns that might be dominating to make the signal seem so clean. And so that's one of the problems here, is in terms of the velocity structure, you could run into either one of these cases, but the spectrum width can sometimes help you out with that, whether it's really noisy or in this case, it's unusually low, because if you look in some of the areas around it, this is an area of strong low-level shear, and you probably expect a little bit of turbulence, so you would expect those spectrum width values actually be quite a bit higher than in that little area we're seeing the contamination. And also, if you've been looking at this data and kind of talking amongst yourself, you might have noticed this little feature. We'll talk about that here in a little bit. So just kind of put a pin in that, and we'll come back to it. So those are just some of the common features. And so, that can be a lot. We're talking about 6, 7, 8 things. It can be hard to remember all that. And so one of the great things about the work that Jamie and Evan did was they came up with this 3-step process trying to simplify things. And so now I'm going to step through what that is just to help you out. And then afterwards, I'm going to pull up a cloud instance with some data to kind of step through it in more of a live example. And so the first thing we recommend people do is try to identify where the circulations are and see if they make sense physically with what we know about storm structure. So just to help things out a little bit, I drew this line in here to give a sense of where the reflectivity gradient was, so we know where the stronger returns are, where the weaker returns are. And so now that we know this, when we highlight this area that looks a little off, we can compare it to where it is with the rest of the storm structure and think, maybe there's some sidelobe contamination going on here because we've got those weaker reflectivity returns. So then from there, what you do is to go look at the velocity texture. And so in this particular case, on the bottom, I have that same example I showed on the last slide, but I wanted to compare it to a good example. So this example number 1 is what we would expect to see in a legitimate circulation, both in terms of its location as well as the velocity structure. And so that's a good example. In the lower one, when we look at it and we look at the velocity structure, again, we've got that really elongated shear zone that doesn't look natural. You have a little bit of a maximum near that in those inbounds that are questionable, but really you've got a broad area there of say 45, 60 knots. You don't see that nice natural tail off in the velocity values as you move away from the circulation center. So again, it's that texture to it that just doesn't look right. And so between the location being off and the texture not looking right, it looks kind of blocky. This would make me think that this is definitely a imposter circulation. And that's what they tend to look like. So from there, we would move on to step 3, which is we're just trying to identify that we have a likely source for the sidelobe contamination. We're not necessarily trying to do a super thorough analysis because, I mean, obviously when you're doing this, everything's time sensitive. You just want to confirm that what you think is contaminated, that you have a likely source for it. And so in this particular example, it looks a little different because I decided to put GR2 up where everything else were AWIPS image captures. And so you can do this sort of thing in AWIPS using all tilts, but the simple fact of the matter is right now we don't really have a good cross-section tool. So if you can identify the region using all tilts, you can kind of go up and look at the data. And like in this particular case, you can see we're getting some contamination obviously from above. And if I showed all the tilts between here, you could see even between above and horizontal, you've got some really strong reflectivity returns in there that could be positively contributing from the side lobe. And so you can definitely do it, but it's not necessarily as easy as, say, pulling up a cross-section. And the one thing about GR2 Analyst right now is it does give you the ability to kind of cut across that region and see what's going on quickly. And so in this case, I've highlighted an area here with this white outline where the main lobe is going to be here towards the middle where the reflectivity returns are really weak. In where the side lobes are likely going to be located, you have a lot of really strong returns, certainly a lot of 40 to 50 dBz, but you also have quite a bit of area in that 50, 60 dBz. And so lots of potential contamination sources there. So we feel pretty confident not only that because of just looking at the data, it looks like it's contaminated, we can also see a source region for it too. And so at that point, we feel like we could say, okay, we need to just discount that and look at everything else. And so that's where we go. Once we identify data as bad, we really encourage forecasters to ignore the bad, lean into the good, and make the best decision you can. So since this is PowerPoint, I can just kind of pretend like I can just draw, like put a blindfold over the bad data so that it can help me ignore it. And so a few slides ago, I said, let's put a pin in this. So now we're going to take the pin out and talk about it. Because once you kind of visually block out the data that you know that's bad, there's all kinds of good data here that can still help you make a warning decision. So if we look in the hook echo here, we can see we've got a significant circulation. We've got rotational velocities of 35 to 40 knots. And when we look at CC, we can see indications of a tornadic debris signature where we've got those really high reflectivity returns. So there's still plenty of data here that if for some reason you hadn't had a warning out, you could certainly get it out now. More likely what the case would be, you would have already had a warning out, and then now you could do an update on it, possibly even change wording to radar confirmed if you didn't have reports. And so there's still plenty of good data here. And that's really the big thing, because that's, I think, with the newer forecasters that we put through RAC, they tend to struggle with the fact that if you do have that contamination, their natural tendency is like, well, oh, it's contaminated, I don't warn on it. And it's like, no, you still probably want to warn on it if the other data suggests it. And so that's something we really try to convey to them so that they feel comfortable with it. So before I wrap things up today, I do want to just do the one case from the cloud instance. And so with that, I wanted to give you just the quickest run through of the environment I felt like I could. So I've got these screen captures here with the convective day one outlook where you can see we've got moderate risk. If I focus in on just the tornado, you can see we've got the 15% hatched. And so high risk of tornado, definitely significance on the table. We also have a trough approaching from the west. So definitely a good setup situation. Because it is February, we have what we would call seasonally significant instability. So we've got around 1,000 joules of mixed layer Cape, and the shear is significant. Deep layer 70, near low levels around 40 knots. So kind of that typical low Cape, high shear type of winter situation. So definitely a favorable tornado environment. So with that, and so I've got the storm in question here. And this is a storm I talk about in our rack ILT. And one of the things I like about it, besides the fact that it's got a clear sign of contamination, it's got a lot of other issues too. You know, working with newer forecasters, we like to give them some of those textbook easy signatures, but you also need to mix in some of those more questionable ones because you don't want them thinking it's always real easy. So this is definitely one of those cases. So this storm in question here, it's got fairly decent supercell characteristics, at least in terms of reflectivity up here in the upper left. So, you know, you got a really strong core, lots of high reflectivity values in the core, likely associated with hail. And then you kind of got this elongated hook, maybe not necessarily the most classic looking hook because it's just so long and stretched straight, but definitely the hook appearance to it. And if we zoom in just a little bit more, but when we look at the storm relative velocity, we can see here in the upper middle that we got some features in this velocity data that just don't look right. But before I get that, let me also look at the location of it. So if I put my mouse over it, just so you can kind of see where the center of this circulation is out in the clear air away from where the hook echo, or at least kind of more the tip of the hook echo is. So it just doesn't necessarily look the way it should. Realistically, you would expect to see something down here. Now, in this particular case, it does look like there might be something down here, but I suspect in addition to the sidelobe contamination, we're having some real issues with the velocity de-aliasing as well. They're probably going hand in hand. So I'm not even sure I believe what's going on down here. But before I go there, let me just look at the velocity data to kind of analyze this texture just to make sure I feel like it is sidelobe contamination. So if I click on some of the areas in here, you can see we have, 50 knots there. There's another 50 knots. There's 55, so it actually gets a little stronger there. But we've got generally this big, broad area, 45, 50 knots. And then as you get a little closer to the hook, there's some higher values here. But even with this, you're still getting a little ways away from where the actual hook echo is located. So it just doesn't look right. Texture doesn't look right. So it definitely seems to be a candidate for sidelobe contamination. So I'm going to just zoom out a touch just so we can see things a little better. Because the storms, as you can tell from the storm motion, I mean, they're moving at almost 60 knots, so they're moving fast. So, and this is one of the tricky things in AWIPS too, is because the storm's moving so fast, as you even tilt up just a few degrees, this storm is already going to displace quite a bit. And so it's not always going to be the easiest thing as you go up to see where the potential source region is. But as we go up to say 1.8, see 1.3, even here starting at maybe 1.8, you can see we've got some really high reflectivity values, certainly in the mid-50s. And even here, much broader as we go forward. So 2.4 and even up into 3.1. So there's definitely a lot of really strong reflectivity data that side lobe could be hitting. Whereas at 0.5, what we're looking at is pretty much sub 10. 5 to 10, there's a 3 dBz. So it's a pretty broad area where the reflectivity is pretty weak. So I meant to point this out earlier. I had this text up here just to help with those 3 steps. So first thing, identifying the circulation location, then analyzing the velocity texture, and then looking for that source. So in the process of doing this, we noticed that the circulation is not quite in the right place. The texture of it doesn't look good, and there's obviously places where that contamination could be coming from. So we feel pretty good about that. But then the question then becomes, in a case like this, well, what would you do about a warning decision if you didn't have a warning out at this point? And what I really try to encourage people to going through rack is that you have a day where it is a favorable tornado environment. The reflectivity structure definitely looks like supercell, and I didn't point it out earlier, but if we go up even here to say 1.3 degrees, and if I sample, we're at about 6,300 feet, 68 if you do mean sea level. But you can see here, at this point, the velocity data looks more like you would expect it from a legitimate circulation. So there's clearly a mesocyclone even at, say, 6,000 feet. And so all the data we would look at with this suggests that this storm is very capable of producing a tornado. So you definitely would want to warn on it. It's just you want to make sure you're making that decision based on the good data, not the bad. And so just to kind of wrap this up, this is 21:24. If I move just about 12 minutes ahead of time, this is where now we're finally starting to see something good. If we look in the Hook Echo region, the velocity data looks much better. I still have a little bit of imbalance because I think the STI average probably isn't the best for this particular storm. It might be moving a little slower, maybe a little more to the right. But it still looks pretty good in terms of the way the circulation should look. And also, if we look at where the reflectivity is higher here, we've got 42 dBz, we've got really low CC, and even our ZDR is low. So we have indications of a debris signature. And so by leaning into what data is there and it's good, you could definitely get your warning out before it was obvious that something was going on in this particular case. But because between the sidelobe contamination and even the velocity de-aliasing issues, it's certainly not a clear-cut, simple situation, especially for somebody who's maybe not the most comfortable at looking at these things. So with that, let me go ahead and let me just wrap things up, talking a little bit just in terms of our training and future plans. Besides this issue, because we got this training out about 18 months ago. The next thing we're wanting to address is looking at wind farms and how it causes velocity contamination. And I know the folks there at Central Illinois have already done some work on it. So they've already shared their slide deck and some other materials with me, which is a great help. And so I'm hoping to get a lesson together in RAC on that at some point this calendar year. We've had a little bit of issues with BAS, who hasn't, but that's a whole nother story. But that has impacted some of our training delivery schedules. And so, but certainly sometime this year, we're hoping to get a lesson out on this. Likewise, one of the things I've been meaning to do and just haven't had a chance yet is to go back to some of our other lessons that talk about some data quality artifacts and look at some of the other sources of contamination that was found in that Bentley paper from 21 and just make sure that we're hitting that adequately. And so we're hoping to make any updates we feel like are needed there in our current training. And the last thing I'll just say before I wrap things up and open up for questions is our RAC training, we're constantly involving it, but for the folks out there, people are probably all across the spectrum. Some folks probably went through RAC. Some may have gone through when it was DLOC, or some may have even gone through when it was the ops course. And so just letting people know the way things are with RAC right now, we really try to break up the lessons into nice digestible chunks as much as we can. And so there's a lot of things listed here, but all of these lessons take anywhere from, say, 5 to 30 minutes. So it makes it easy, or at least easier, if you have a shift and maybe, it's not an X shift, but you've got a little bit of quiet time, maybe you could work on something like this. We try to make it as easy as possible to access the content. Likewise, at least in terms of radar principles, a lot of this is tied to the radars themselves. And so whenever there is a new radar build update, we try to go in, analyze the CCRs, we talk with the folks at the ROC, and figure out, okay, what are going to be the issues that most impact operators, and then try to make those updates in our RAC lessons to abide by that. So that's a fairly routine process that we're going through about every 12 to 18 months. So with that, I think that's all I have. So I'm available for any questions that folks have.
All right, thank you, Andy, for a great presentation. So now we're opening it up into the Q&A. One came in while you were talking, Andy. It's just more of a comment, but this person said they've seen cases where the displacement is even worse with the higher number of sales scans. Can't remember if that came in while you were discussing the displacement as you went up, but yeah, it can be even worse than what you should.
Yes. And so this particular example I showed, I think it's sales times 3, but yes, it definitely can. Absolutely. And that makes things challenging. And that's why I bring up that thing with the cross-section, is because even with that cross-section does make it a little easier. I wish we had a better tool in AWIPS right now, that unfortunately we don't.
All right, one just came in. Does a mid-level circulation have to exist in order to see a false circulation due to sidelobe contamination at 0.5?
That is a really good question, and the answer is no. I hinted at this in the presentation, but I had a conversation with Jamie, and one of the things that she had mentioned was what they've been finding and having conversations with forecasters is a lot of times when people are looking for that source region, they want to kind of match up the velocity in the contaminated area with some other velocity value, like a 1-to-1. And a lot of times that's just not there. And I mean, there's all kinds of things too when you get these different velocities placed in a different location in terms of, like, if you get a lot of convolution with other data, that can mess up the power spectrum in a way where what you see in the main lobe that's contaminated be very different than what's actually coming from the contaminated region, especially once 2 DVDAs had a chance. I think that can have a role in it as well. I think that's part of what the problem is with the one cloud case I showed, is you get that area near the middle of the circulation and 2D VDA just doesn't know what to do between the strength of the circulation and the contamination. So it's like you're getting like multiple regions that are all blocky and different looking. But you certainly don't need that mid-level meso. You could have a storm that doesn't have mid-level rotation and it gives the appearance of a low-level circulation.
Thank you for that explanation, and definitely an important question to ask. All right, the next question that came in is, when doing the cross-section for side lobes, does that get confused with a BWER, or bounded weak echo region?
The confused is the hard part to me, because it's when you have a storm with supercell structure and it's got a BWER, that seems to be the prime candidate for when this is going to happen. Just the nature of it, it just makes it that much, you have more source contribution possibilities if that makes sense. You know, especially if, like the example I showed, where you get those really strong reflectivities that fill in the weak echo region as you move up to that closer mid-level updraft. So yeah, I mean, I think that's definitely a source possibility, is when you do have a well-defined BWER, you'll see a lot of that potentially get into the contamination at low levels and mess things up. Doesn't have to be a BWER, but when you have it, I think it just makes it more likely. Hopefully I made that clear.
Yeah, thank you, Andy, and thank you for the question. You briefly touched on this during the presentation, but just to give you another chance to talk about it, is I noticed the presentation is called Elevation Side Lobe. You mentioned it used to be called maybe vertical side lobe or horizontal. Do you want to just talk about the change in the naming convention, or a little bit more about that?
Yeah, so one of the things, just in kind of doing the research on this, is side lobe contamination has been something I know we've talked about at least a little bit in our training for a while, but I think the emphasis early on was more in those horizontal situations where you'd see almost kind of like that horn off to the side of a storm. And then I think we just, over time heard more accounts of what people would describe as vertical side lobe contamination. And I know in talking with Jamie, I think her and Evan, they specifically went with that naming convention of elevation side lobe contamination, because in talking with people, they were thinking too orthogonally. They just were thinking, well, it's horizontal or directly above. And one of the things that I think was getting lost on forecasters is that pretty much anywhere along that side lobe around the main lobe could be contributing. So it could be almost off at a 45-degree angle, and it could still be causing significant contribution. And so I think that was their philosophy for going with the naming of calling it elevation side lobe contamination. You still hear it called vertical side lobe contamination some too, and it's not necessarily wrong. And it, again, I think I mentioned this when I was on that slide, you know, especially if you do start seeing it at, say, 0.9 or even 1.3, sometimes the contamination is actually occurring at a level below 0.5 if the radar's seeing high enough into the storm. And so it's all kinds of places where that contamination could be coming from. And so it just seems like calling it elevation side lobe contamination kind of opens people's minds to that a little bit better.
Yeah, that makes sense. It makes sense that it's kind of a broader term and less limiting, I guess. And I think that graphic that you showed from the paper was very helpful to kind of understand that it's kind of a donut that surrounds it and can be anywhere in that donut.
I just want to thank everybody for your time and attendance. We had a pretty good group show up, and I know people's time is full, and there are positional challenges in terms of staffing and things like that. So I just really appreciate people taking the time to show up today.
Yes, absolutely. This is a well-attended session, so I think everyone was very interested in the topic. So thank you again, Andy, for presenting on it. And as we discussed earlier, our last one of these WDTD-led sessions is going to be April 24th, where Andy, again, will be presenting, and it'll be on scanning strategy best practices, so things related to VCPs and the like. So if you're interested, please tune in for our April session, and then after that, we'll kick things back off into kind of the field-driven series. So if you have anything you'd like to present on, May is when we'll kick off again on that type of series. So please, we're always looking for presenters. Feel free to reach out if you have a topic that you're interested in. But once again, thank you all for joining us today, and we look forward to seeing you in April. Have a good day, everyone.
Thanks, everybody.